Hello and welcome to part 3 of this Homework 1 video series. In this part of the homework, we're given a problem in which we have a cylindrical barrel filled up with some fluid level. So here's the drawing of the cylindrical barrel, and this rectangle here at the top signifies the top of the fluid level. So everything below here is the fluid that's filled up in the barrel. So what we're asked to find is, hey, what is the pressure force that is exerted on each of the circular ends of the cylindrical barrel? And also, what is the pressure force that the fluid exerts on each of the cylindrical halves of the barrel, so the sides of the barrel? First, if we want to take a look at the pressure force that is exerted by the fluid on each of the circular ends of the barrel, what we can do here is we can put in an imaginary plane in the middle of our barrel and split it into two. So I'm going to try to draw this as best as I can. So we split the barrel up into two sections, basically putting a rectangle down the entire middle of the barrel. And the idea here is that if we can find the pressure force that the imaginary plane here exerts on the end of the cylindrical barrel, we can then transform that into the pressure force that the fluid exerts on each of the ends of the cylindrical barrel. So what is the pressure force that the imaginary plane exerts on each of the ends? Well, we'll have that the force is equal to the pressure times the area. And since pressure will be changing dependent upon the fluid level, this will be dA. So we'll have a differential area here. Now what we'll want to be doing here is adding this up to get obviously the total pressure force that this imaginary imaginary plane exerts on the ends of the barrel. So what we can say here, if we have H as our fluid height here, so H is the height of this fluid, we can see that the area here will depend upon it'll depend upon where we're at in the fluid level. So if we know that the barrel is of length L, this dA will be L times the change in height of the fluid. This is dA. So dA equals L times dH, which makes sense because it's going to be different depending upon whether we're at the very top of the fluid, middle, or the bottom of the fluid. So that's why we would have our differential change in height there. Now what we can also say here for this pressure, and this is what transforms this into not only what is the pressure force that the imaginary plane exerts on each of the ends, but what is the pressure force that all the fluid exerts on each of the end. Well, there's something that, I have learned it as the term hydrostatic pressure. And essentially what that means is, okay, when we have a container and that container has some fluid in it, what is the pressure that that fluid exerts on the walls that the fluid is in, so that the container the fluid is in. So what that is that the pressure that fluid exerts on the walls that the container in is the density of the fluid times the gravitational constant G, and that is multiplied by the depth of the fluid, or H. So what we can do here is we can substitute both of these in, and we now have an expression for the pressure force exerted by the fluid on each of the sides of the wall. So we have F equals to the integral. Again, we want to add all of this up. So rho GH, substituting that in for the pressure of the fluid here, and then multiplied by LDH. Now, what will be our integration, our bounds of integration here? Well, we'll be going from our fluid height here, so we'll be going from 0. So if we say 0 is at the top or bottom, it really doesn't matter. We'll be going from 0 to H, which is the height of the fluid. So integrating this, we end up with F equals L rho G. And what we should do here, because we have H as one of our limits of integration, we should make these now dummy variables of integration so that we don't get them confused, because they are definitely not the same. We have our constants out here, so the length times density times G, and this will be H prime squared over 2, and we will be evaluating this at 0 and H. So the pressure force that the fluid exerts on each of the ends of the cylindrical barrel is just equal to the length of the barrel times the density of the fluid, gravitational constant G, times the height of the fluid squared over 2. So this is the answer to number 1. What is the pressure force that the fluid exerts on each of the cylindrical ends? So now what we want to move to is a little bit more challenging of a concept, is the pressure force that is exerted on each of the cylindrical halves of the cylindrical barrel. So now that we have found the pressure force that the fluid exerts on either end of the barrel, so here and here, we now want to find the pressure force that the fluid exerts on either of the sides of the cylindrical barrel. So I have drawn here a view looking down the end of the cylindrical barrel. So on either side here will be the sides of the barrel that we want to find the pressure force for. So this approach is a little bit different, but we want to start with the pressure force expression that we had before, which was integrating the pressure times the differential area. However, this time what we can use is polar coordinates here. So you see I have drawn this view here, and what we can do here is that if we have this angle here, we know that theta here is equal to 0, and this angle here, we'll just call it theta 1. We do not know this angle, but if we draw this down here to the middle of the circle here, we'll call this theta 2. We know that this is negative pi over 2. So what we need to do here is express our pressure force equation here in terms of theta, and then we can integrate from theta 1, which we don't know, and theta 2 in order to find the pressure force on one of the sides of the cylindrical barrel. So to start here, the first thing that we will need to figure out in order to do this integration is we need to have our limits of integration, so theta 1 and theta 2. So we need to find out, okay, what is theta 1? Well, what we can say here is that since this is the height of the fluid, this line at the top here, this is H, so that's the height of the fluid. So this right here, so we know that this is our radius, so we'll call this R, this is our radius R. So this right here, that dotted line that I just made, that is H minus R. So this is the height of the fluid minus the radius of the circle that we've drawn here for the barrel. So what we can do here is we can express our theta 1 now. And remember, this is our theta 1, so this is the angle that we're looking at here, this angle. So what we can see here, draw this over to the side, is that theta 1, well, it'll equal the arc sine of H minus R over R. So I have the arc sine, so sine of negative 1. H over, or H minus R, then divided by R here. Okay? So now that we have theta 1, we can take a look again at our force expression here, our pressure force expression. So we have limits of integration, and we'll just keep moving our way down. So let's take a look at pressure here. So we know that pressure is equal to rho GH. However, we can plug this into our integral here that we're making, because our limits of integration are in theta. So we need to figure out how we can express H in terms of theta. And this is it's not very intuitive, but once I write it down, it'll make sense. To express h and theta here, so we need to express this in theta. So what we can say here is that h is equal to r. So we have the height of the fluid, so it's equal to r here, plus what we can say here is that this here, this is kind of small, but this is equal to r sine theta. This area inside that angle that I have drawn there. So we have r here, and this, if we add on r sine theta here, that will give us our entire h, which is the height of the fluid here. So we have r sine theta, and we now have an expression for a height in terms of theta. So that will allow us to plug it in for our pressure here. But the next thing we'll have to look at is this differential area here, dA. So to deal with the differential area here, I'm going to draw another picture here, down here. And essentially what we have here is we'll still have our angle here. But what we have is we want to split this up into little strips to find the differential area on one side of the cylindrical barrel. So we have some differential height for each of these. So it'll change in height. And we also have some length from the middle of the barrel to the outside of the barrel. So we need to express both of these, dH and L, which will give us the differential area in terms of theta. So to express L in terms of theta, well, that's rather easy. Since since R here is our radius, so R is our radius, so this is just the radius that we have created for the end of the cylindrical barrel, and we have this as our theta. So again, this is theta, and theta is going all around the one half of the cylindrical barrel, and it could go around the other half as well. So we have R and theta. Well, L going down all of the side of the half of the barrel will just be R times the cosine of theta, since this right here is the width of the circle. So L here, so we have P. Actually, I'm just going to go ahead and write this below it. So we have our width here is equal to R times the cosine of theta, because it'll just be below our theta. Now, we also had to express this dH in terms of theta as well. And this is actually rather straightforward, because we, for our pressure, we had to express H in terms of theta. So to get dH, all we have to do is integrate this expression here. So if we integrate this, so dH will be equal to R cosine theta. The integral of sine theta is cosine theta. So we will have dH is equal to R cosine theta. So again, just to reiterate, we had to express all of this integral in terms of theta. So we found our limits of integration first, because we needed to find theta 1. And to express pressure in terms of theta, we know that pressure is equal to rho GH. However, H needed to be expressed in terms of theta. So we found our expression for H by using our diagram here. And we also needed to express the differential area in terms of theta as well. And we know that the width all the way up one side of the circle is R cosine theta. And that the differential change in height, the little strips that we have drawn, so the height would be vertically, would just be taking the integral of the expression we already found that has H in terms of theta. So now that we have everything expressed in terms of theta, we can go ahead and just plug it in and evaluate our integral. So we'll have our write everything for the integration here on the right hand side. So we have our pressure force is equal to the integral. So we have pressure, and we know that this is a rho GH. Let me take rho G out because they will be constants. So we'll have rho G. This is times the integral of H, which H is H is R, the radius, plus R cosine theta, okay, which we have derived earlier. And this will be multiplied by our differential area, and our differential area here we know is the differential height times the length or the width of the circle here. Well, we found the width and we found the differential height, so this will be R squared cosine squared theta. D theta, this again just multiplying R cosine theta by R cosine theta with multiplied by differential height. And our limits of integration here, we will be going from theta equals 1. Again, we know what that is. Theta equal theta 1, not theta equals 1. Theta 1 is the arc sine of H minus R over R, and theta 2, which is negative pi over 2. Okay? So we're actually going to be using Wolfram Alpha a little bit to integrate this, because there's a couple of places. One, we would have to do integration by parts 2 times, but I'm going to go ahead and what we can do is we'll have an R cubed term in both of these here. So I have rho G times R cubed, and this is multiplied by the integral from theta 1 to theta 2 of cosine squared theta. And from here, we'll have our next integral here, which, let's see, will be the integral, again, from theta 1 to theta 2. And this time we will have sine theta times cosine squared of theta. Sine theta cosine squared of theta. I don't think I made any mistakes here. So I did write everything correctly here. I didn't write my d theta here, but we get the point. I went ahead and plugged both of our integrals here into Wolfram Alpha. And the integral of cosine squared here is theta over 2 plus 1/2 sine theta cosine theta. And the integral of sine theta cosine squared theta is negative 1/3. So instead of adding, I subtracted 1/3, and this will all be multiplied by the integral, which continues to be cosine cubed theta. So what we need to do here is now evaluate with our theta 1 and theta 2. Well, we can see here for our cosine terms, when it's theta 2, so it's negative pi over 2. Okay, I'll write, so theta 2 equals negative pi over 2. Cosines equals 0. Our theta 1s, our theta 1 is the arc sine of H minus R over R. So what we need to do here is express our theta 1 in terms of cosine here, so that we can then evaluate it. So expressing this in terms of cosine, so, well, first, I guess if we want to really draw it out, we can see that sine theta 1, excuse me, is equal to H minus R over R. So if we wanted to find cosine of theta 1, using the trig identity of sine squared times cosine squared equals 1, we can see that cosine squared would be the square root of 1 minus sine squared theta. Evaluating this further, we can put sine or theta 1 there. Evaluating this further, we will get plugging in our sine theta 1, which is h minus r over r. We'll get, so for the 1 here, we will have r squared. We'll have r squared on the bottom, and we will subtract h minus r squared from that. Again, our r squared and r squared will give us our 1, and then just plugging in our sine theta 1 here. So we now have our cosine theta 1. And again, when theta is 2, our cosines are 0. So I'm going to go ahead and erase this here. Try not to make this video too long, so I erased what we had for our cosine 1 and just put it as an aside here because I'm running out of room. But if we want to go ahead and evaluate the final expression, plugging in for both of our limits here of integration, we'll have the pressure force F is equal to rho g r cubed, and then evaluating. So if we plug in our first term here, we'll have a negative pi over 4. Our second term here, cosine of negative pi over 2 is 0. So going to our next, we'll have negative 1/2 arc sine of h minus r over r. And we'll have another minus 1/2 arc sine of h minus r times our cosine 1 theta. And we can actually go ahead, we have our side here. I'm going to condense this numerator down a little bit more. So we can have here r squared minus h squared minus 2hr plus r squared. So we see here that the r squareds cancel, and we are left with 2hr minus, because we have the negative on the outside, h squared. Okay, so this will be multiplied by the square root of 2hr minus h squared, so all under the square root, over r, just taking the square root of r squared. So that's for our first term. We evaluated at theta 2 and theta 1. Now for our second term, we will have negative 1/3. And then again, plugging in our theta 1 here, we will have square root, or we won't have square root, we'll just have, we'll be raising it to the, let's see, 3 over 2 power. So we'll have 2hr minus h raised to the h squared, raised to the 3 over 2, and then this will be divided by r cubed. So that's it. This is our expression here. Very long and drawn out when we evaluate these integrals here, but the main point, and I know the camera can't see it right here, was the setup of how we get the pressure force when we need to express the pressure and differential area in terms of our polar coordinates theta. But this is the expression here for the pressure force that is exerted on the sidewalls of the cylindrical barrel. And up top here, I'm not sure if we can see it, but we, at the beginning of this video, derived the expression for the pressure force on either of the circular ends of the barrel. So that will conclude this video. We have answered both of these questions. So thank you for watching.